Hello everyone, welcome to this presentation. My name is Matt. I'm a structural engineer at SRAM Software in Vancouver, British Columbia. And we're going to give you a high-level overview of how you can calculate connection design forces within SRAM. We're going to look at ways that you can automatically create pass-through force components based off of the members that are connected to one another and the orientations of each of those members. We're also going to look at situations where you might want to group certain members that contribute to a force at a joint, connection component essentially, like a gusset plate, and then you can tabulate those forces and sum them up and review them afterwards. We're also going to look at how you can view this information once you obtain all your connection design forces, viewing them graphically or numerically. So in this presentation here, we're going to talk a little bit more about pass-through forces, or what some people might refer to as transfer forces. We're then going to look at how we can determine different ways that a member might contribute to pass-through force calculations or contributions. And we'll have a short example that we've grabbed from an AISC design example guide that we'll present to you as well. At the end of the presentation, I'll wrap things up with a few summarizing points and open up the floor for you guys to ask any questions you have. And in this presentation, we're going to be using SRAM, our structural analysis tool. SRAM software does also offer different types of material design, foundation design, timber, concrete, you name it. So if you're curious about any of those, we'll have some more information about how you can access our website at the end of the presentation. So what are pass-through forces? Basically, you can think of them as the loads that are produced at the end of a member transmitted across a joint in your structure. And they'd be used to calculate the forces across a joint in your structure from the different member contributions. So maybe we have this red member, this red beam, and this green brace contributing to a connection, like a gusset plate or something similar. We could then determine what the forces are across that joint, which would represent that gusset plate in your model based on the applied loads. And these are the loads that must be communicated to the connection designer. So SRAM itself won't do the connection design, but we are able to calculate these forces for you, and that can be sent to another application or a spreadsheet that would be able to do the connection design. And the beauty of this is that SRAM can calculate these for you, regardless of how large your model is or how complex your model is. So we're going to look at a couple different ways that we can model these contributions to a pass-through force component, like a connection. The first one that I'm going to talk about here is user-defined connection components. And basically this involves a user specifying pass-through force IDs that are assigned to member ends. And those member ends are chosen based on which members might comprise a certain connection. So maybe you have a certain connection like this one here that has 3 bolts on the flange, or sorry, the web of the connecting beam. And you can assign that pass-through force ID number 1. And any other location in your structure where you'd like to have that same connection style, you can use that same pass-through force ID. And an SRAM will then be able to sum up all the forces that have that same pass-through force ID and give you the worst and the best case scenarios for those groups of member pass-through force IDs. So then you can look at an envelope of forces that are coming in for that type of connection and ensure that whatever type of connection you've designed will be able to resist those loads. So again, these are used to group connections that may be similar, and SRAM will be able to accumulate the member end forces and transform them to the joint's orientation. So if you have a rotated column, that won't necessarily mean that you have to have all those forces in the global X, Y, and Z axis. They can be in whatever orientation you like. And just to explain this a little bit better here, I have an example model that I'm going to just work with for the next little while. And where we would define this sort of information is using the pass-through force tool. This tool here in the geometry window. And if I left click on this tool, you can see that I have this option in the data bar to specify which members have what type of pass-through force ID. I just select the pass-through force ID. I also have this option to auto-generate the pass-through groups, which I'll show you more on later on in the presentation. But if I zoom in here, I can see that I've already assigned some pass-through force IDs. So at the end of this member here, and I'll just toggle on the display of my member numbers. So member 11 and member number 1 here have pass-through force ID 1. And so that's saying that I want those two members to basically calculate the member end forces, make sure that they're all in the same orientation, and give me the summation of those across this joint here. And this joint happens to be joint number 1. I then have member pass-through force ID number 2 that's assigned to a different group of members, these two right here, and they're going to be contributing to pass-through forces across this joint. And we can work our way across the model. Now on the other end of the model, I've also got some other things going on here. So you can see that I've got basically the same model, but it's just been rotated slightly. And the only change that I had to make here was I just wanted to rotate my joint coordinate system, which is very easy to do using the user coordinate system tool. I can just make sure that I have the orientation of the joint matching the orientation of my desired connection components. And this way, when I look at the pass-through force IDs, which happen to be the same contributions, pass-through force ID number 1 to these two members here, that will be all with respect to that orientation of that joint. So it's not going to be doing it in the global XY because it's changed the orientation of the whole structure. So I'm going to go ahead and run the analysis now. Just run a linear static analysis. We get a clean solution, and now I can look at the results. So here I can look at the results for individual load cases. I also have some load combinations as well. And if I just want to look at the results of one specific location, I know where the member force ID, pass-through force ID ones are. They're these two members right here. I can just left-click on the Show Connection Design Pass-Through Forces tool. And I just need to tell it here, I want to look at the pass-through force assembly method that's called by member pass ID. And I'm just looking at pass ID number 1. And I can look at basically filtering this the same way we would be able to do with the reactions tool. So here, for this particular load combination, I can see them getting 24 kilonewtons, almost 25 kilonewtons of forces transmitted across this joint in the X direction. Then I have the Y direction, the Z direction, and in different rotational reactions as well at this location. I can also sum up different load combinations, so I have 3 in total. So I can say, let's look at load combinations 1 through 3, and maybe I'll get some different results. So I have 24, Fy is 4.2, and Fz 18. So in this situation, it doesn't look like, it looks like load combination number 1 was actually the governing for every single direction for this particular joint. But if it wasn't, and there was different load combinations that had different governing directions, so maybe I have more forces in the Y for load combination 2 than number 1, those would all be shown here. It would show me the maximum. So this doesn't necessarily have to be in equilibrium if we're looking at load combination ranges. So this is pass-through force ID number 1. We can see the same thing over on this other model. And if I just rotate this, you can see that when I look at Fx, for example, it's with the orientation of the member that I want it to be with. So even though it's a different, slightly rotated model, I can still make sure that these are all transformed to the correct orientation of the joint. You can look at Fy and the different rotational connection design forces as well. Now moving a little bit further along here, if I want to look at pass-through force ID number 2, which is at this joint, we can see that we get a whole other set of forces. And the reason we might want to have different joints with the same pass-through force ID is that we might have a situation where we want to try to borrow the same connection design for each one of these joints. If we can utilize the same connection design in different locations in the structure, we're going to save ourselves money. We're also going to save the contractors and detailers a lot of effort. So we can just make sure that we have all those forces calculated so that we know what sort of forces we're going to get for a specific type of connection. We can also view this numerically. If I go to the numerical results window and I look at the results for connection design pass-through forces, here I can see at each joint, the pass-through force IDs, the load combination. I'm just looking at number 1 right here. But we can look at all load combinations if we'd like to. We can also look at a summation of the pass ID ranges. And so here we'll be able to see what sort of forces we're getting, the maximums and the minimums. And we have to make sure that our connection design satisfies those criteria. The method that we talked about right now, it gives you full control over which members are contributing to the connection. So if you had a gusset plate at a specific joint, you could calculate the forces exerted on that gusset plate by just telling S-frame which member pass IDs belong to that particular connection. And again, the forces contributing to those members are summed up at a joint with respect to that joint's orientation. And we can look at the maximum and minimum forces for those shared connection types, considering different types of loading and different joints where those same connection types may occur. And this is using the more manual method for assigning member pass IDs to individual member ends. There's also the automatically generated connection design component method. It's a bit of a mouthful here, but it is very powerful. So SRAM can actually automatically group members to form connection contributions for you based on the geometry that's connected to a specific joint. So you can easily calculate pass-through forces for your entire model without having to go through and assign member pass IDs to each individual member end. And it's based off of connecting members in each direction. So you may remember I looked at joint number 1 in that previous example. That's the joint at the top corner of one of my structures, this one right here. And you can see that we have multiple members connecting to that joint. We have member number 7 coming in at an angle. This is in the y-axis. Member 11 is coming in at a brace. It's a brace, sorry. And it's coming in at a diagonal to the x and y-axis. We have member 1 in the x-axis, member 31, and member 14. So basically how this works here is it's going to use the geometry of the members that are connecting to your specific joint. And you can imagine this if you were to draw a hemisphere, or let's say a contact lens even, at the specific joint you're looking at. You can say that we're looking at the positive x direction. So we're going to draw a hemisphere pointing in the positive x, and any member that connects through this hemisphere is going to be contributing to that specific group that's automatically generated for us. It is going to ignore anything that comes completely orthogonal to that direction. So that's why 7 and 14 aren't included, but we have 11, 1, and 31 that are automatically included. But you can always override this afterwards if you want to. It gives you a good starting point, and for a lot of people it might be perfectly fine to continue on with this, but if you want to override it, again, it's not set in stone. So let's look at this approach now. Here, if I go back to the geometry window, and I just remind ourselves here, I'm just going to switch tools. So I was talking about joint number 1 before. That's this joint right up here. And the members that are connected are 7, 11, 1, 31, and 14. Now if I use this pass-through force tool, and I actually right-click on this tool, I can see that it's automatically generated different connection groups for me automatically. So for every single joint that is detected in the model, I can left-click on a specific joint, and it's going to show me in the positive x direction. Maybe I'll just make this a little bit bigger. We have the member number 1, which is this member right here. I'm showing my pass-through force IDs, so it might get a little bit crowded here. But member number 1, member number 11, and member number 31, which is this brace here. Those are connecting the positive x direction. In the negative x direction, which is in the opposite side, you can see the orientation of my x-axis. We don't have any members connected, which makes sense. In the positive y direction, we have member number 7 and member number 11. And the positive z, we have some bracing and our roof beam. So that's 7 and 11. And the negative z, we have 31 and 14. So 31 is this brace here, and 14 is the top of the column. And it's going to try to give us these groups for us automatically, and it's going to suggest different types of connection types based off the geometry and also the member end connectivity. So if it's a pin versus a fixed connection. These are just suggestions. You can always override it with anything you like, but these are the ones that come within the design guide that we've used. You can also create your own if you like, and these are just basically suggestions that can then go to the detailer to give them an idea for what they might want to use. So now if I run the analysis again, I'm just going to click Run Analysis and run a linear static analysis. We're going to look at the results for those specific sets of connections. So look at it graphically first, and I'm going to look at the Show Connection Design Pass-Through Forces tool. And maybe I'll look at the load cases this time. So I can look at the forces for the pass-through force assembly method. That's by design group name. I'm going to look at the component in the positive x direction, which we already know. We have a positive x contribution to this specific joint here at number 1. And I'm going to say look at the positive x where we have 3 members contributing. So any specific joint where we have 3 members in the positive x contributing, we're going to have this type of design group. And now I can see that I have 2 different sets of joints here in this vicinity that have that same group. And I can look at the directions. In the x direction here, I have different forces at different levels. The y direction, the z direction, and obviously we have our connection design moments. Just like before, we could sum this up for different load cases. So I believe I have 6 load cases. So I'm going to say let's look at the total for load cases 1 through 6, and it's going to define the worst case scenarios for those different groups. So for fx, fy, fz, and so on. You get the idea. We get the same thing on the other model, which again has automatically been translated to the correct orientation based off of the rotation of this model. And we can view the information numerically as well. So if I look at the results for connection design pass-through forces, you can see that now I have a lot bigger spreadsheet. I'm not using the pass ID method anymore. This is unchecked, but it's showing me at each individual joint, I have different design groups based on the orientation and the number of members that are contributing. It's going to suggest a specific type of connection and the forces that are contributing, and I could look at different load cases and combinations if I wanted to as well. So we have a lot of ways to control this. And the advantage of using this approach versus the manual approach where we assign pass IDs to specific member ends is that this allows us to quickly and easily group our members in our entire model that would contribute to a specific connection. We can also specify connection types and custom group names if we wanted to. This might help pass the information along to the connection designer to the intention that the engineer might have for these connections. And of course, we have full control over the contributing members and everything that goes into these design groups. The original suggestions that they have are just that. They're just suggestions that the user can then override. So now we're going to look at a quick example, calculation example. And this example actually came from an example guide from the AISC. So for a bit of background, it's an industrial structure, and it has vertical and horizontal braces, and it's 2 levels. So here's the top level. And we can see here that we have a diaphragm representing the floor system on the top level. We have some I-beams or Y-flange shapes representing the columns, and they're spaced at 25 feet in each direction. And we have a 100 kip load applied to this diaphragm. On the bottom floor, we have an 80 kip load that's applied, and you notice that we actually have some horizontal and also some vertical bracing on this bottom floor. So this is the second floor. Now we're actually going to look at 3 different bracing arrangements. So the same model, but 3 different alternatives using different bracing arrangements. So this bracing arrangement A here, you notice has this vertical bracing just on the right side, between member line 2 and 3. For B, we have it distributed, you can see here in the top left and the bottom right, according to this orientation view. I'm looking at the elevation. And for the option C here, we have, I guess, more of an aligned brace here. But you can see, again, it's in the top left and the bottom right. Just the orientation of the braces has changed. And we're going to just focus in on looking at the results for this particular joint in each model. So we're going to look at the joint basically where the beam line 2 and column line 2 intersects. So in this guide, they actually go through the calculation of all the forces. So I'm going to just detail that here. These are the forces that are entering the beams from the diaphragm and the horizontal bracing. So again, this is the elevation view. It is a 3D structure that we'll look at later on. But you can see an idea for the different forces that are represented within this model. Obviously, with different bracing configurations, we're going to get different forces in different places. And ultimately, we're then going to look at the transfer forces and the axial loads in the beam. So the transfer forces, or pass-through forces, as we've referred to them already, are the forces that are being transferred through the joints that represent our connection. So again, I'm just focusing in on these very middle joints here. So for this particular joint on bracing configuration A, on the left-hand side, we have a transfer force of 20 kips. In the middle, for bracing configuration B, we have a transfer force of 70 kips. And the same thing here on bracing configuration C. So I'm going to use S-frame and use the member pass ID method to try to come up with something similar. Now, just a reminder, this is a 3D structure, and we do get contributions from both the vertical and horizontal bracing. So just looking at option number 2 here as an example, we're looking at, I guess, different orientations. So this is the beam. We're looking down in plan view, and this is an elevation view. So we can see that we do get contributions for specific joints from the bracing as well. That wasn't really easy to illustrate in those last images. So I wanted to include those as well to see that there are some forces coming from the braces and from the beams, obviously. So you can get an idea for what those forces might be. So I'm going to go into SRAM now, and I'm actually going to open up a different model that was already created for me, so I can go through and actually just work with this exercise a little bit more. So if I go to the geometry window, turn off the display of my joints, I can just walk you through, I guess, a bit of an illustration of what this represents. Look at the front view. We have a diaphragm in the top of each one of these structures. We've also had to estimate some of the properties that weren't available within this guide. So some of the exact loading and or section properties and so on, they weren't given, so we had to estimate them as much as we could to the best of our ability. But basically, what we want to just highlight here is that if we look at the pass-through forces tool here, and I show the member contributions, I'm just going to unhide the pass-through force ID. I can see that I have a contribution at this specific joint. So I've assigned pass-through force ID 1 and 1 here as well. So basically we're looking at the forces coming from this horizontal brace and this beam that are going to be transferred through this joint. The same thing on this other model that has just a slightly different bracing configuration. So we're looking at the forces from these two members, the brace and the beam, that are transferring through this particular joint. And this model has a different bracing arrangement, as we can see here. Let me just change the orientation of my view. Maybe it's a little bit easier to see in 2D. So we have our horizontal brace contributing, but we also have this vertical brace contributing and our beam. And if I look at my loads, I just want to make sure that you're aware that we've represented this the same way we described in those PowerPoint slides. So I have 100 kilonewton or 100 kips or a load at the top of my structure. It's applied to the diaphragm. And I've distributed the 80 kip loads on the second floor to each panel here, or each bay essentially. So we're getting essentially the same thing that we modeled within the hand calculations. Now I'm going to go ahead and run the analysis, or run a linear static analysis. And I'm going to look at some of the results. So I'm going to look at the axial forces first of all. And we can get an idea for the total axial forces within each of our members. I can look at the maximums at any one location. I'm using a fair amount of decimal digits. Let me just change that here. We don't need that level of precision here. But you can get an idea for the axial forces within each one of these braces and the beams and columns as well. What might be more interesting to me is looking at the connection design pass-through forces. So I'm going to click on this tool here. And I'm going to look at the pass-through force assembly method by pass-through force member ID, specifically looking at pass-through force ID 1, which we've already discussed, and I'm looking at the FX contributions. So here I can see that for this particular bracing configuration, which is A from the PowerPoint slides, we have 20 kips of pass-through force ID or transfer force. For B, we have 70 kips. And the same thing for C, which matches the values that we got from that design example guide. So that's what we wanted to see. We wanted to see that the values were matching the hand calculations that matched the value that the AISC design example guide used for calculating the transfer forces or pass-through forces through the specific joint. Now we're just looking at it at a very small scale, looking at it on one joint in each frame arrangement. But as you can imagine, it scales up quite easily once you get the entire model structured modeled. So that brings us to the end of today's presentation. So hopefully through this presentation, you saw that you can basically set up any type of connection with different members connecting to contribute to the forces at a connection. You can have it automatically create pass-through force groups for you. And the member end forces that are contributing to a connection component are going to be then transformed automatically and combined to establish design forces suitable for that connection component. And you can view this information graphically or numerically. You can look at the maximum and minimum forces for a specific pass-through force ID that might have multiple joints within the model, but you want to look at the worst and best case scenario.